Good evening, everyone. So, in this session today, we'll be discussing about the different AC circuits, right? So, before discussing about the AC circuits, we'll briefly discuss about the concept of the phasor, right? We'll give a brief concept about the phasor diagrams, right? So, what actually phasors are, right? These are actually the vectors in XY plane, right? Which represents the instantaneous value, right, of the current and the voltage in an AC circuit, right? So they give us the instantaneous value of current and voltage in an AC circuit, right? So these are actually the vectors represented in XY plane, right? And with the help of which we can find the instantaneous value of the current as well as the voltage, right? So the phasors are nothing. These are the vectors representing the current and the voltage in an AC circuit, right? Which are drawn in an XY plane, right? And the vertical component of these vectors actually gives us the direction, gives actually us the magnitude instantaneous value of the current and the voltage, right? So let's suppose that the voltage is EMF is given as E is equal to E naught sine of omega t, right? Sine of omega t. Now you can see this is an AC voltage, right? E is equal to E naught sine of omega t represents an AC voltage, where E naught is the maximum value of the AC voltage here, right? And omega is the frequency and t is the instantaneous time, right? So if we substitute the value of t for any instant, it will give us the value of the instantaneous value of the EMF, right? AC voltage. So now the concept is this: we can more generally write it as E naught sine of omega t plus phi as well, right? We can write it as like this. We are adding a constant to this omega t term, right? And this phi is what we call as the initial phase, right? This phi is what we call as the initial phase. And this complete omega t plus phi, we call it as total phase, right? We call this as total phase. So this is the total phase, and the total phase of voltage or current gives us the instantaneous value of the current or voltage and direction of alternating quantity as well, right? Or the direction of the current and voltage as well, right? So phi is the initial phase, omega t plus phi is the total phase. So phi is nothing, it's the initial phase. So phi will actually give us the value of the voltage at time t equal to 0, or we can say it can give us the values about the current or voltage at time t equal to 0, or initial value of current or voltage, right? That's why we call this phi as initial phase, right? So mathematically omega t plus phi is nothing, it's an angle, right? But physically it signifies that it gives us the instantaneous value of the current or voltage. Apart from that, it also gives us the direction of the change in current or the direction of the voltage, right? At that instant, right? So phi is the initial phase, right? And omega t plus phi, we call it as total phase. Now the concept of phasor diagrams is that it actually simplifies the concept of the AC circuits, right? It simplifies the solution of the AC circuits, right? We can easily actually see how the current and the voltage varies and how the current and voltage behave in an AC circuits, right? That's why we use the concept of the phasor diagrams, right, in AC circuits as well. So phasor diagrams are nothing; they are representing the current, alternating current, and the alternating voltage, but of same frequency, right? But of same frequency, right? And they are act as vectors in xy plane. You can see here we have two vectors here, I naught vector and v naught vector, right? So these are the phasors. This is the phasor for current and this is the phasor for voltage, right? Let's suppose that if the voltage is v is equal to v naught sine of omega t, right? V naught sine of omega t. It means that it will make an angle of omega t with the x-axis, right? X-axis. So this vector will be drawn in such a way so that it makes an angle of omega t with the x-axis, right? So this will be the maximum value of this vector, that's v naught. The length of this phasor vector, the length of this phasor actually represents the maximum value of the quantity, right? Maximum value for quantity. the length of this phasor vector will actually represent the maximum value of the current, and length of this phasor vector will represent the maximum value of voltage. Similarly, if we have current like this, that's equal to I is equal to I naught sine of omega t plus phi, right? Sine of omega t plus phi. So it means that it will make an angle of omega t plus phi with the x-axis, right, of this diagram, right, or of this plane, right. On this plane, it will make an angle of omega t plus phi, right. So this is the total angle for the current, and this total angle is nothing. This is the omega t plus phi with the x-axis, right. So this is also called as the total phase of this current, right, and the total phase of this voltage is nothing, it's omega t, right, omega t. Now let's suppose for voltage, phase is phi 1, that's equal to omega t, right. This is the total phase for the voltage, and phase for the uh, current is nothing, that's equal to omega t plus phi, right. Then the phase difference between them will be phi 2 minus phi 1, right. That will be equal to omega t plus phi minus omega t, right? Minus omega t. So that will be equal to phi. So the phase difference between the current here is current and voltage here is phi. Or uh, we can say that you can see here the phase total phase of the current is more as compared to the total phase of voltage. That's the reason we say here the current leads the voltage, right. Current leads the voltage. Or we can say that the vertical component, this is the phasor, right. If we draw the vertical component or the projection of this current I on the y-axis, similarly if we draw the projection of this v naught on the y-axis, we get the projection of this current on the y-axis will give us that's I, that's sine of this component, that's I naught sine of omega t plus phi, right? Sine of omega t plus phi. So an instantaneous value is nothing. It's the vertical projection of the current or voltage on the y-axis, right? Similarly, we get the value of V instantaneous voltage as V naught. Its projection on the y-axis will be V naught sine of omega t, right? So this is how we can calculate the instantaneous values using the phasors, right? Using the phasors. Similarly, here you can see here this is the voltage, right? This is the voltage here. V naught is the voltage and I naught is the current here, right? I naught is the current here. And you can see here the phase difference between the current and the voltage is actually phi. Or we can say current leads here, right? Leads the voltage by a phase of phi, right? So this is the concept of the phasor diagrams, and all these diagrams will be all these circuits, AC circuits, will be discussed one by one using these phasor diagrams. So the conclusion is that phasor diagrams actually are the vectors, right, which represents the alternating current or alternating voltage on XY plane, right? The projection of these alternating currents or the alternating voltage on Y-axis gives the instantaneous value of the current or voltage, right? And the phase difference between them tells us about which quantity is lagging and which quantity is leading with respect to each other, right? Now let's discuss this lagging and leading of concept a bit in detail, right? So let's suppose we have this voltage V is equal to V naught sine of omega t, right? V naught sine of omega t. And if the current is, suppose I is equal to I naught sine of omega t plus phi, right? Sine of omega t plus phi. So you can see here, if we calculate the phase difference between them, that's delta phi, that will be phi 2 minus phi 1 here. So it will be actually omega t plus phi minus omega t, that will be equal to phi, right? So it means that phase difference between the current and voltage here is positive, or we can say that current leads voltage, right? Voltage. What does it mean, current leads voltage? It means that current attains its maximum value first, then voltage, right? So current will attain its maximum value first, then the voltage, right? So current will reach its maxima, will reach its maxima first, then voltage, right? Then voltage. So that's what we actually mean by the concept of lagging and leading. Or we can also say that here voltage is lagging, right? Voltage is lagging. Voltage is lagging behind current. Voltage is lagging behind current, right? Voltage is actually lagging behind current. So similarly, if we have this equation here that V is equal to, right, V naught sine of omega t, right? And we have current equation I is equal to I naught sine of omega t minus phi, right? Sine of omega t minus phi, omega t minus phi. And this is the equation, right? Then the phase difference between them will be delta phi, and this delta phi will be nothing. This will be phi 2 minus phi 1, right? Phi 2 minus phi 1. That's equal to omega t minus phi minus omega t. That's equal to minus phi. Or we can say here, actually, the current is lagging behind the voltage, right? Current is lagging behind the voltage. So voltage is leading here, right? Current is lagging behind the voltage. It means that the voltage will reach its maximum first, then the current, right? Current is lagging behind the voltage, right? So this is the concept of leading and lagging, right? Which quantity is leading and which quantity is lagging. That's the concept of the leading and lagging in case of AC circuits, right? Now let's discuss these phasor diagrams and these analysis of these AC circuits one by one. We'll be starting with the analysis of pure resistive AC circuit. Let's discuss the pure resistive AC circuit, right? You can see here the EMF or the voltage across the alternating voltage or varying voltage across this pure resistive circuit is E naught sine of omega t, right? E naught sine of omega t. So E is EMF across this pure resistive circuit. That's E naught sine of omega t, right? Omega t, correct? If we calculate the current is nothing. It's the EMF upon the resistance, right? That's E upon R. That's equal to E naught upon R sine of omega t, right? Sine of omega t, correct? Sine of omega t, correct? So if we write this value I here, I will be actually equal to I naught, right? Sine of omega t, right? And the value of this I naught is nothing. It's actually equal to the maximum value of the current through this pure resistive circuit, that's E naught upon R. So maximum value of the current of this pure resistive circuit is E naught upon R, right? So let's suppose if we divide by root 2 on both sides, if we divide by root 2 on both sides, that will be I naught upon root 2, that will be equal to E naught upon uh, root 2 R, right? Root 2 R, correct? So you know that I naught upon root 2, E naught upon root 2 is the RMS value of a AC voltage, RMS value of a AC current for the complete cycle. For the complete cycle, it's the RMS value of current and RMS value of voltage. Or it means that we can replace this I naught by root 2 by the concept, by the term IRMS is equal to ERMS upon R, right? ERMS upon R. So this is very important, right? This is very important here. This is a very important conclusion with respect to the pure resistive circuits, that IRMS is equal to ERMS upon R, right? So now moving on further, right? Moving on further, let's suppose if we plot these two what we call as these two quantities, one is current, another is the voltage, right? On the same curve, right? On the same curve, right? So let's suppose we're plotting this value of this current, right? The value of this voltage, it's E naught sine of omega t, right? So it will be a sinusoidal, right? Like this. It will be a sinusoidal voltage like this. So this will be the function of this. This will be the graph for this AC voltage, right? This will be the graph for this AC voltage. So this is the graph for this AC voltage, right? And this is the maximum value of this AC voltage, that's E naught, right? That's E naught, right? And this is minus E naught here, right? Minus E naught, right? So this will be the time period for this AC voltage, right? This will be the time period for this AC voltage. You can see here the frequency for the current and the voltage is same, right? Now, if we plot this current here, you know that current is E naught upon R, that's sine of omega t. But the amplitude of the current here is less than the amplitude of voltage, because there is a factor of R, right? There is a factor of R, right? Let's suppose this R is greater than 1. If R is greater than 1, then the amplitude will be less than the AC voltage here, right? So we can plot the same graph, right? Same graph on this. Let's suppose this represents the current, right? So the current will behave, it will have the same time period. Current will behave like this. The current will behave like this. This was our AC voltage, right? This is our AC voltage, and this is our current. So this will be the behavior of current, right? So this is nothing. This is the voltage, right? This is the voltage graph, right? And this will be the current. This is nothing. This is the current. So this is how the behavior of the. It means that here you can see that the phase difference between the AC current and the voltage here is zero, right? It means that they are in phase. They are in phase, right? They are in phase. What does it mean? That they will reach their maxima and minima at the same time, right? They will become zero at the same time. The current will become zero at the same time. Voltage will become zero at the same time. They will become maxima at the same time and minima as well at the same time. That's the concept of being in phase, right? Now, if we draw the phasor vectors for them, right? If we draw the phasor vectors for them, you can see here the voltage and the current here, right? The voltage and current here are in phase, right? It means that their phase difference is zero, or we can say that the current makes an angle of omega t with respect to x-axis, and the current also makes the angle of omega t with respect to x-axis. So you can see here they are both aligned at an angle of omega t with respect to x-axis, right? And the maximum value of this current is I naught, right? That's here. This is I naught vector, right? And the maximum value of this E naught is voltage is E naught. So this is the maximum value of E naught. So this is the phasor diagram for this AC voltage and AC current for the pure resistive circuit. This is for pure resistive circuit, right? So this is for the pure resistive circuit, right? Now let's discuss the AC circuit containing pure inductor, right? Pure inductor. For a pure inductor, we have to see how the behavior of current and voltage is for the pure AC circuit. So here E is equal to E naught sine of omega t, right? E naught sine of omega t. So this is for pure resistive circuit, pure inductive circuit, right? For pure inductive circuit, this is the value of what we call as supplied AC voltage, right? And we know that in case of inductor, since the current is varying, and the voltage is also varying, so the current will also vary. And because of that varying current, there will be an induced EMF. There will be an induced EMF, right? There will be an induced EMF in this inductor, right? Induced EMF will be there because of the varying current in this inductor. And we know that this uh, induced EMF is nothing. It's equal to minus L di by dt in case of pure inductive circuit, right? Pure inductive circuit or pure inductor, right? Now applying the Kirchhoff's voltage law, right? Voltage law. So E plus EI should be equal to zero, right? E plus EI should be equal to zero, and E is E naught sine of omega t, right? E naught sine of omega t, and the value of induced EMF is uh, minus L di by dt, right? Minus L di by dt, That should be equal to zero. That should be equal to zero, right? That should be equal to zero. Now you can see here, if we take this E naught on the LHS, right, and L di by dt on the RHS, right? Now we can integrate it, right? We can integrate it. So it will be E naught upon L sine omega t, right? dt, and on the LHS, on the RHS, we will have Gi, right? we'll have di, right? Now we can integrate it on both sides, right? From 0 to t. Let's integrate it from both sides from 0 to t. So it will be 0 to I, right? The integral of di will be I. So this will be the current across this inductor, right? So integrating it on both sides, we will get E naught upon omega L, right? And cos of omega t, right? Cos of omega t with a negative sign here, right? With the limits 0 to t, right? With limits 0 to t. So it will be equal to I. So the value of current I will be, we can write it as minus E naught upon omega L, right? Cos of omega t, right? Cos of omega t. So it will be equal to cos of omega t, right? From 0 to t for at any instant, right? For at any instant of time, this will be the value of what we call as the current, right? Current, or we can write it as equal to E naught upon omega L sine of omega t minus pi by 2, right? Sine of omega t minus pi by sine of omega t minus pi by 2. We can write the value of current as E naught upon omega L sine of omega t minus pi by 2, right? So this will be the current, right? This will be the current through the inductor, right? This will be the current through this inductor. So value of I comes out to be equal to E naught upon omega L sine of omega t minus pi by 2, minus pi by 2, minus pi by 2, right? So this is the value of what we call as current through this inductor, right? We can see here, if we write this equation, we write this equation as I is equal to I naught sine of omega t minus pi by 2, right? Omega t minus pi by 2, omega t minus pi by 2. Now this I naught has the value equal to E naught upon omega, E naught upon omega. Now if we compare this equation I naught with, if we compare this equation I naught with what we call as voltage upon the resistance, right? Resistance. It means that this omega L actually behaves like a resistance for this inductor, right? It behaves as a resistance for this inductor, and this we call as XL, right? XL, we represent it as XL, that's equal to omega L. And this resistance offered by this inductor, we call it as inductive reactance. We call it as inductive reactance, right? So this is nothing, this is the inductive reactance of this inductor, right? Inductive reactance of this inductor, right? And omega is nothing, is the frequency, right? Omega is nothing, is the frequency, or we can write it as omega is the angular frequency, that's 2 pi frequency times L, right? So this is the resistance, inductance, reactance, resistance offered by this inductor. We call it as inductive reactance, and it depends upon the frequency of this input AC, right? The frequency of this input AC. It means that if frequency is equal to 0, if frequency equal to 0, right? If frequency is equal to 0, right, then value of XL will be equal to 0, right? Value of XL will be equal to 0. It means that for zero frequency, right? For zero frequency, actually the value of XL will become 0, and I naught will become infinity, right? I will become infinity. It means that it will offer an infinite resistance to the current which is having, to the voltage which is having a zero frequency, right? For zero frequency current, it offers what we call as infinite resistance, right? It actually offers infinite resistance. So you can see here, the value of XL was omega L, right? It was omega L, right? E naught upon omega L, right? Okay, so it means that XL is 2 pi times frequency into L, right? 2 pi times frequency into L. If the frequency is 0, right? If frequency is 0, then XL will be 0. So it will be infinite resistance, right? Current will be infinite, right? Current will be infinite. If current is infinite, it means that resistance will be behave like a zero resistance, right? Where resistance will be behave like a zero resistance, or we can say it will behave like a short circuit, right? It will behave like a short circuit, right? It will behave like a short circuit, right? It will behave like a short circuit for a zero frequency, right? So the concept property of this inductor is that for very small frequencies or frequencies approaching to zero, it actually behaves like a short circuit, or the current flowing through this inductor is huge, right? It's a huge current, right? Now talking about the phasor diagrams, right? Phasor diagrams. You know that we know that E is equal to E naught sine of omega t, right? E is equal to E naught sine of omega t, and the value of current is nothing, that's equal to E naught, that's I naught sine of omega t minus pi by 2, right? Sine of omega t minus pi by 2. Now, if we find out the phase difference, now if we draw the vectors for both of them on the xy plane, you can see vectors for both of them on the xy plane. So this is here, it's like a omega t minus pi by 2, right? Omega t minus pi by 2, right? So this is the if this is omega t minus pi by 2, it means this will be the current, right? This will be the vector, phasor vector for this current, right? And for voltage, we have, for voltage, E naught and I naught with respect to the pure inductive circuit. In this case, the current, right? Voltage leads the current, so the phase difference is pi by 2, right? Phase difference is pi by 2, or we can say voltage leads current by pi by 2, by pi by 2. So the voltage in this circuit actually leads current by an angle of pi by 2, right? By an angle of pi by 2. So this was with respect to the pure inductive circuit, right? Now let's discuss the pure capacitive circuit, right? Let's discuss the pure capacitive circuit. Now, in case of pure capacitive circuits, you can see here we are supplying an AC voltage of is equal to E naught sine of omega t, right? Sine of omega t. And the capacitance of this capacitors, let's suppose C is the capacitance for this capacitor, right? And we know that at any instant, the potential difference across the ends of this capacitor will be E, right? E, right? And we know if the charge Q is supplied to this capacitor, then this charge Q is nothing. This is equal to C times V, right? And the voltage supply is E naught sine of omega t. So it will be C times E naught sine of omega t, right? Sine of omega t, correct? If we have to calculate the value of current, we have to take the first derivative of this charge, instantaneous charge with respect to time. So it will be C times E naught, right, upon omega cos of omega t, right? Cos of omega t. But we can also rewrite it as C times E naught upon omega sine of omega t plus pi by 2, right? Sine of omega t plus pi by 2. We can write it like this as well, so that we can compare it with the voltage, right? So this is the value of current, right? This is the value of current. Now we can write this current as that's equal to I is equal to C, that's equal to I is equal to I naught sine of omega t plus pi by 2, right? Sine of omega t plus pi by 2. The value of I naught is nothing. This is the maximum value of current, that's C E naught upon omega, right? This is the maximum value of the current, or I naught, right? So we can say there amplitude of the current is C E naught upon omega, right? That's the maximum value of the current, right? And the phase difference between the current and voltage is E is equal to E naught sine of omega t, right? E naught sine of omega t, and the value of current is I is equal to I naught cos of omega t, right? I naught I is equal to I naught sine of omega t plus pi by 2, right? Omega t plus pi by 2. So here once again the phase difference current current, right, and the voltage is pi by 2. That's delta phi, that's equal to phi 2 minus phi 1, that's equal to pi upon 2, right? That's equal to pi upon 2. That's equal to pi upon 2. So this is the phase difference, or we can say here in this case current leads voltage in case of capacitor, right? Current leads voltage in case of capacitor, leads voltage in case of capacitor, right? In case of in case of capacitor. Current leads voltage in case of capacitor, right? And you can see that if we plot the vectors phasors for these two quantities, potential voltage and the current, right? So the angle which the voltage will make with the x-axis will be omega t, and this will make an angle of omega t plus pi by 2. It means if this is omega t, then 90-degree angle will be there between 90-degree angle will be there between the current I and the E naught. And you can also see that the value of the magnitude or the maximum value of voltage is greater than the current, right? So these are the two vectors, two phasors for voltage and current, which are at an angle of 90-degree. We can say that current actually leads the voltage by an angle of pi by 2, right? By an angle of pi by 2. Now further discussing it, we got the value of current as C E naught upon omega, right? This was the maximum value of the current. Now if we compare this with the voltage, compare this with the V upon R, right? V upon R. So from here you can see here, if this is V upon R, right? We can say, just a minute. The value of I here was it was C E naught, right? C E naught, and integrating it will be cos omega t upon omega C E naught upon omega, right? So C E naught upon omega. So now calculating the value of resistance, we compare between this and this, we get the value of resistance here. That's 1 upon omega C. 1 upon omega C. 1 upon omega C will be the what we call as resistance, right? This will be the 1 upon omega C for this case, right? So you can see here, the maximum value of the current is C E naught upon omega, right? C E naught upon omega, or we can say that the R we also represent it by XC, or the value of XC is 1 upon omega C. We call it as capacitive reactance. This is nothing. This is equal to capacitive reactance, right? This is nothing. This is equal to capacitive reactance. Capacitive reactance. That's equal to 1 upon omega c, 1 upon omega c, right? So we can write it as xc as 1 upon 2 pi f c, right? 2 pi f c. Or you can see that if the frequency is 0, right? If the frequency is 0, then the value of xc is tends to infinite, right? Infinite. Or we can say the value of I tends to 0, right? Or we can say frequency is 0 for DC currents. This is 0 for DC currents. So it means that the capacitor actually blocks the DC currents, right? It easily allows the flow of AC currents through it, but capacitor blocks DC current, right? Capacitor blocks DC current, right? Blocks DC current, right? Capacitor blocks DC current. So DC current is blocked by the capacitor, because for DC currents, for DC, for DC frequency is actually equal to 0, right? Frequency is actually equal to 0, right? Now if we plot between resistance and the frequency for this capacitor, right? If we plot between the frequency, reactance, and the frequency for this capacitor, right? Then this will be the behavior of this impedance, right? So this is the frequency versus capacitance impedance graph, reactance graph for this pure capacitive circuit, right? So in case of pure capacitive circuit, we concluded that current leads as compared to the voltage, right? Now let's discuss about the combination of the AC elements, right? Combination of the AC elements. So first combination that we'll be discussing is RL circuit. That's the resistance and inductor circuit in series, right? Resistor and the inductor circuit in series, right? So let's suppose I current is flowing through it, right? And we are supplying an AC is equal to E naught sine of omega t for this series resistance, right? For this series circuit. So they are in series, so the current flowing through them will be same, right? Current flowing through them will be same. Let's suppose the potential difference across this resistor is VR, and the potential difference across this inductor is VL, right? So VL is the potential difference across inductor, and VR is the potential difference across what we call as potential difference across resistor, right? That's the VR. And we know that in case of a pure resistor, the phase difference between the current and the voltage is zero, or it means that uh, current and the voltage in case of pure resistive circuit, they are in phase, right? They are in phase. So that's the reason, if this represents the current through the resistor, then this will be the phasor direction of the phasor for pure resistor as well. So this will be the direction of VR, right? This will be the direction of VR, right? And we know that in case of pure inductor, the voltage lags the current by an angle of 90 degree. So that's why this vector will actually represent uh, the VL vector for this, or phasor for this VL voltage, right? Because we know that for inductor, the voltage leads the current by an angle of 90 degrees. So there has to be an angle of 90 degree between the current and the voltage, right? So this is the this is the what we call as angle between VL and VR. So VL and VR are at 90 degree, right? Now the resultant of this VL and VR will give us actually the uh, value of this E, right? Value of this E. So if we find the resultant of these like a vectors, we know whenever two vectors are perpendicular to each other, their resultant is given by under root of A square plus B square. Similarly, the resultant of VL and VR phasor will be given by E is equal to under root of VL square, VL square plus VR square, right? VL square plus VR square, VL square plus VR square. So this is the resultant, right? Or we can say that this is the value of E, right? This is the value of E, and the current flowing through them is same, that's I, or we can write VL as I into XL, right? I into XL whole square, right? I into XL whole square. Similarly for resistor, it will be I into R whole square, right? I into R whole square. So this will be equal to, I will be taken as outside, right? Will be left with under root of XL square plus R square, right? XL square plus R square, right? Or we can write the value of current here equal to what we call as value of current will be E upon, it will be E upon under root of XL square plus R square, right? XL square plus R square. So it will be E upon under root of XL square plus R square. This will be the value of current through this circuit, right? This will be the instantaneous current. Now the maximum value of this current will be I naught, that will be equal to E naught, right? That will be the maximum voltage, that's E naught upon under root of XL square plus R square. So this will be the maximum value of the current, right? Maximum value of the current. Now the angle of this resultant E with respect to this current I, right, will be tan of phi, right? That will be given by the tan of phi. So tan of phi will be nothing. It will be VL upon VR, right? VL upon VR will be the tan of phi, or we can write this equal to as XL upon R as well, right? So this will be the tan of phi, or we can say we can find the phase difference between the potential difference voltage and current as phi. That will be equal to tan inverse of VL upon R, or we can find this phi equal to tan inverse of XL upon R, right? XL upon R. So this will be the value of phi, right? This will be the value of phi, and you can see here the value of phi is positive, right? It means that for this input voltage, the voltage will lead the current, right? E leads I, right? We can say that E leads I by an angle phi, right? E leads I by an angle of phi, right? By an angle of phi. So E leads I by an angle of phi, right? So E leads I by an angle of phi. Now you can see that the effective resistance was here. This behaved as an effective resistance R, right? Effective resistance R, right? Effective resistance R, right? We call this resistance, represent this effective resistance with Z, right? Z. Now it means that the value of Z will be nothing. It will be equal to under root of XL square plus R square, right? And this resultant resistance we call as impedance of a circuit, right? This is nothing. This is what we call as impedance of a circuit, right? Impedance of a circuit. So this is the impedance of a circuit. It behaves like a they behave like a phasors, right? R and XL are at 90 degree with each other. The resultant will be given by under root of XL square plus R square, right? So this is the concept of this is how we calculate the current through the series LR circuit, and how voltage is leading the current, right? Or the phase difference between the voltage and current, and the total resistance or the total impedance of a circuit, that's under root of XL square plus R square. So this is the total impedance of this LR circuit. Now let's move on to the RC circuit, right? Let's do the similar calculations for the RC circuit as well, right? For the RC circuit as well. And in case of RC circuits, you know that in case of RC circuit, the current leads as compared to the voltage, right? Current leads as compared to the voltage, right? And for pure resistive circuit, uh, for the pure resistive circuit, right? For the pure resistive circuit, you can see for the pure resistive circuit, the current and voltage are actually in phase, right? If this is the phasor for current, then the direction of the phasor for this voltage across the resistor will be same, right? So this is the direction of the phasor. And we know for capacitor, the voltage across the capacitor, let's suppose the voltage across capacitor is VC, and the voltage across the resistor is VR, right? VR. And VC is will be perpendicular to VR, right? VC will be perpendicular to VR, because in case of capacitor, current leads, right? Current leads. So if this angle is 0, then this will be minus 90 degree angle, right? So it will be in this direction, right? So this will be the resultant EMF, and this resultant EMF will be nothing. This resultant EMF will be once again, this resultant EMF will be once again nothing under root of VR square plus VC square, right? VR square plus VC square, VR square plus VC square, VR square plus VC square. So this will be the resultant EMF, right? And the current through them will be same. That will be equal to I, right? That will be equal to I. So it means we can once again write it as uh, I times XC whole square, right? Plus I times R whole square, right? Or the E will be equal to I times XC square plus R square, right? Or the value of current will be E upon under root of XC square plus R square, right? So this will be the value of current, right? This will be the value of current. So the maximum value of current will be once again I naught, right? Maximum value of the current will be I naught. That will be equal to E naught upon under root of XC square plus R square. And similarly, we can write this I equal to E upon Z, right? E upon Z. The value of this Z is what we call as capacitance, what we call as impedance of the circuit, right? That will be equal to under root of XC square plus R square, right? This is once again the impedance. This is once again the impedance. So this resistance we call as impedance, right? So this will be the impedance of the circuit, right? And once again this tan of phi will be given by VR, right? VC upon VR, right? So tan of phi, the angle of tan of phi will be equal to VC upon VR, right? VR, VC upon VR, right? VC upon VR. And this tan of phi here will be once again equal to XC upon R, right? XC upon R, C upon, correct? So this is the discussion of what we call as pure RC circuit, right? So you can see that in case of RC circuit, here current leads the resultant voltage, right? Here I leads the current, right? I leads the current, I leads the voltage by an angle of phi, right? by an angle of phi, by an angle of phi. So it leads the voltage by an angle of phi, right? So this was about what we call as resistance and capacitor, right? RC circuit, right? Let's move on to the final circuit, right? That's the series LCR circuit, right? Now we have all the three circuits in series, all the three elements, electrical elements, right? Or AC elements in series, right? You can see resistor, inductor, and capacitor as well. So that they will have the common current flowing through them. That's equal to I, right? And the potential voltage supplied by this uh, to this circuit is E is equal to E naught sine of omega t, right? This is the voltage supplied to this circuit, right? This is the voltage source, right? Now, once again, you can see that the same current will flow through them, right? Same current will flow through them. And once again, the current for if VR is a voltage across the resistor and VL is the voltage across the capacitor, sorry, inductor, and VL is the VC is the voltage across the capacitor, right? Now VL will be perpendicular to the current because VL is leading the current by an angle of 90 degree. VC will be perpendicular to the current but in the downward direction because current is leading the VC by an angle of pi, right? Current is leading the VC by an angle of pi, right? By an angle of pi by 2, not pi. By an angle of pi by 2 or 90 degree, right? By an angle of 90 degree. VL leads I by 90 degree and VC lags behind I by an angle of 90 degree, right? Now, once again, so the resultant of this VL and VC, we can write it as VL minus VC if VL is greater than VC, right? If VL is greater than VC, and we can write the resultant of VL and VC, right? VL and VC, they will have a resultant along this. Let's call that resultant as VL minus VC, right? Now this VL by this VC is perpendicular to VR now, right? So their resultant will be like this, right? This will be their resultant, right? And this resultant will be E, right? This resultant will be E. So it means that we can write the value of E equal to under root of VL minus VC का whole square plus VR square, right? VL minus VC का whole square minus VR square, right? Or we can write it as under root of I square, right? I square, right? Multiplied by XL minus XC whole square plus R square, right? R square, right? I square R square, I square R square. You can take this I outside this root. Will be left with I multiplied by this vector that's XL minus XC का whole square, right? Plus R square, right? The value of current I will be nothing. It will be E upon under root of XL minus XC whole square plus R square, right? Plus R square, right? And the maximum value of the current will be I naught. That's equal to E naught upon under root of XL minus XC whole square plus R square, right? And the value of impedance here is Z. That's equal to under root of XL minus XC whole square, right? Plus R square, right? This is the value of impedance. Now let's suppose the angle, the resultant of this voltage makes with x-axis is phi, right? That's equal to phi, right? Let's call this angle as phi, right? Let's call this angle as phi, right? Now, if this angle here is phi, right? This angle here is phi. If this angle here is phi, we can calculate this tan of phi here, right? Tan of phi. Tan of phi can be calculated as this will be calculated as VL minus VC upon VR, right? VL minus VC upon VR, or we can write this phi equal to tan inverse of VL minus VC upon R, right? VL minus VC upon R, correct? And similarly, we can write this tan phi equal to XL minus XC upon R, right? Or this phi will be equal to tan inverse of XL minus XC upon R, right? So the value of total impedance or total resistance offered by this circuit is nothing. That's equal to under root of XL minus XC whole square, right? plus R square. So this will be the total impedance, right? Current we have already calculated, right? Current we have already calculated through this series LCR circuit, right? The current flowing through each of these elements will be same. That will be equal to I, right? This will be the total current, and this is the impedance of this series LCR circuit, right? Now that's it for today, right? In the next lecture we'll be discussing about the resonance conditions. We'll be discussing about the other terms as well, that will be the power factor and wattless currents, and we'll be also discussing the q factor, right? Q factor, that will be done in the next lecture. We'll stop here, meet you in the next lecture. Till then, goodbye and